It's just before 2 in the afternoon on the 1st of April, 2009. A Super Puma helicopter is cruising back toward Aberdeen at 2,000 feet over the North Sea, 11 nautical miles northeast of Peterhead. 16 people are on board. 2 pilots, 14 oil workers heading home after a shift on the Miller platform. The flight data recorder shows everything is normal. Engines normal. Oil temperature normal. The crew is making routine radio calls. 12 seconds. That's all the warning they get. A vibration begins. The chip detector lights up. The gearbox pressure drops to 0. And then, 2 seconds before the recording ends, the main rotor shears off the top of the helicopter and falls into the sea. The fuselage drops 2,000 feet in roughly 23 seconds. There are no parachutes on a helicopter. No glide. No prayer. Just a cabin full of men in survival suits, falling. A crew on a nearby vessel watches the rotor hit the water first, then the helicopter. They hear 2 bangs, then an explosion. Investigators will spend 2.5 years pulling the wreckage off the seabed and rebuilding what happened. They will eventually trace the entire disaster to a single component, the size of a dinner plate. They will issue 17 safety recommendations. The manufacturer will redesign procedures, regulators will sign off, and the industry will say the problem is solved. 7 years later, a near identical Super Puma will fall out of the sky off the coast of Norway. The main rotor will detach and cruise. 13 more people will die, and when investigators tear apart the wreckage, they will find the same broken gear in the same place for almost exactly the same reason. This is the story of how aviation's most thorough crash investigation failed to prevent the next crash, and why the people who died in 2016 were killed by a flaw the industry already thought it had fixed. Before we get into the wreckage, into the chip detectors, into the planet gears that nobody could see were cracking from the inside out, do me one favor: hit subscribe. This channel covers the aviation accidents the major networks won't touch in this much detail, and your subscription is what keeps these long-form investigations on the air. Just one tap, then we'll get into it. Okay, the story begins on a different morning, 16 days before the crash. It is the 25th of March 2009. The same helicopter, registration ending in Lima, has just landed back in Aberdeen after a routine flight to the Miller platform. Engineers at Bond Offshore Helicopters perform a standard end-of-day inspection. They check the oil filter. They check the magnetic chip detector inside the main gearbox. A magnetic chip detector is exactly what it sounds like. A magnet sitting inside the gearbox oil flow, designed to capture metal particles before they damage anything. If a tooth chips off a gear or a bearing starts to break down, the magnet catches the debris. When an engineer pulls the detector and finds metal stuck to it, that is a serious warning. It means something inside the gearbox is degrading. On the 25th of March, the engineers find a particle, a single shard of metal stuck to the detector inside the epicyclic module. The epicyclic module is the upper section of the gearbox. It contains 8 second stage planet gears, each one about the size of your hand, each one transmitting massive power from the engines to the main rotor blades. The engineers know finding metal is unusual. They know it requires a response. So they pull out their troubleshooting documentation. The documentation is a card, a laminated reference produced by Eurocopter, the manufacturer. It walks them through what to do. The card says to test the particle, log the finding, and run additional checks. The engineers do that. The card does not tell them to open the epicyclic module. The card does not tell them to inspect the planet gears, but the maintenance manual does. Buried in the manual is a brief line, almost an aside, instructing engineers to check the magnet rings inside the epicyclic module if metal is found. Those magnet rings sit very close to the planet gears themselves. If a planet gear were starting to break apart, those rings would almost certainly catch additional debris that the main chip detector would never see. The engineers do not consult the manual, they follow the card. The card is what the manufacturer has trained them to use, and the manual instruction was not in the card. Bond does start a process to remove the gearbox entirely and swap it for a unit from another helicopter. They are concerned enough about the metal finding to plan a replacement. But before that swap happens, the helicopter is cleared to fly. It accumulates 36 more flight hours over the next week. 36 hours is not very many. In the life of a helicopter that flies offshore daily, it is barely a few days of operations, but it is enough. On the morning of the 1st of April, 2009, the Super Puma takes off from Aberdeen. The crew flies out to the Miller Oil platform without incident. Some of the passengers on the outbound flight will later report hearing a bang from somewhere on the helicopter just minutes before landing on the rig. They do not report it to the crew. They assume it is normal. It is not normal. Inside the gearbox, on one of the 8 second stage Planet gears, a fatigue crack has been growing for some time. The crack is propagating outward from somewhere on the bearing race. With each rotation of the rotor, the crack grows a fraction of a millimeter further. The bang the passengers heard may have been the moment the crack reached the gear teeth. The helicopter sits on the platform. New passengers board for the return trip. 14 workers from KCA Deutag Drilling, the contractor staffing the rig. They climb in, buckle up, and settle in for the 90-minute flight home. The helicopter lifts off into clear weather. For roughly 50 minutes, everything is fine. Then the chip detector inside the gearbox lights up again. This time it's not a single particle, it's a flood. The cracked gear has finally reached the point where it is shedding metal at a rate the system cannot ignore. But the chip detector warning system on the AS332L2 has a peculiar limitation. There is no cockpit warning specifically for the epicyclic module chip detector activating. The crew gets a low oil pressure warning when the gearbox starts losing oil through the spreading damage. By that point, the gearbox is already in catastrophic failure mode. The cockpit voice recorder captures only 12 seconds between the first sign of trouble and the end of the flight. The pilots do not have time to declare an emergency. They do not have time to attempt a controlled descent. The captain has barely enough time to reach for the radio, the main rotor head and mast, separate from the airframe. The blades, still spinning, fly free. The fuselage, no longer attached to anything that can keep it airborne, falls. A man named Robert Decker, the only survivor of a different North Sea helicopter crash that would happen just 11 days earlier, will later say that survival in offshore aviation is a thin line. The crew of the Bond Super Puma did not get a chance to walk that line. All 16 people on board are killed on impact. The Air Accidents Investigation Branch, the British equivalent of the National Transportation Safety Board, arrives in Aberdeen the same evening. By the next morning, recovery vessels are pulling pieces of the helicopter off the seabed. The rotor head is found about half a mile from the main wreckage site. The cockpit voice recorder is recovered. The flight data recorder is recovered. The gearbox, what is left of it, is recovered. For the next 31 months, investigators will work backward from the wreckage. They will section the gearbox. They will examine each of the 8 second stage Planet gears under microscopes. 7 of them are intact. The 8th is fractured. The fracture surface tells a story. A fatigue crack initiated somewhere in the loaded area of the bearing outer race. From there, it grew, slowly at first, then faster as the gear weakened. The crack propagated until it reached the rim of the gear. It fractured the rim, released the gear, and broke the entire epicyclic module apart in a chain reaction that ripped the main rotor off the helicopter in less than 2 seconds. The investigators determined that no manufacturing defect caused the original crack. They cannot identify the precise origin. The gear simply failed under operational load in a way that the design was not supposed to allow. But the more difficult question is not why the gear cracked. It is why nobody knew it was cracking. The chip detector found metal 36 flight hours before the crash. The investigators conclude that this metal was almost certainly debris from the developing failure. If the engineers had opened the epicyclic module on the 25th of March, they would have found additional debris on the magnet rings. They would have found a Planet gear in distress. They would have replaced it. They did not open the module. The troubleshooting card did not tell them to. The maintenance manual did, but in a way that was not flagged as urgent and was easy to miss. There is a second technical problem the investigators identify. Eurocopter had previously installed a ring of magnets inside the epicyclic module of the AS-332L2 and the EC-225LP. The ring of magnets was meant to capture and hold debris near where it was generated. The unintended consequence was that this ring of magnets reduced the probability that debris generated inside the epicyclic module would ever reach the main chip detector at the base of the gearbox. In other words, the very feature designed to manage debris inside the upper module made it less likely that debris would ever trigger a clear warning at the lower detector. The system was, in a small but significant way, partially blind to its own internal failures. There was a third issue, more about culture than engineering. The maintenance crews working on the Super Puma were experts in helicopter maintenance, but the inside of the epicyclic module was not territory they regularly entered. Opening one of those modules requires highly specialized procedures, the kind of work that aircraft engineers describe as closer to surgery than wrenching. The components inside operate under tolerances measured in microns. Reassembly has to be perfect. Most maintenance organizations send the modules out to dedicated overhaul facilities rather than open them locally. That meant the engineers in Aberdeen, working through a chip detector finding on a Wednesday afternoon, were operating in a zone of partial knowledge. They could see what was on the magnet at the base. They could not easily see what was happening inside the module above, and the documentation system they relied on did not draw a sharp enough line between routine debris and the early warning of a gear in distress. The investigators also discovered something about the magnet rings inside the upper module that should have been the strongest possible early warning. Those magnet rings were never even mentioned in the maintenance manual for the EC-225LP, which uses the same gearbox architecture. The instruction that had been buried in the AS-332L2 manual was simply absent in its sister aircraft's documentation. The Air Accidents Investigation Branch publishes its final report in November of 2011. The report runs to several hundred pages. It contains 17 safety recommendations. It calls for new cockpit warnings, for improved debris analysis, for better chip detection systems, for redesigned maintenance procedures, for fundamental research into how planet gear bearings degrade and fail. Eurocopter accepts the recommendations. EASA, the European aviation regulator, accepts them. The British and Norwegian civil aviation authorities accept them. Service bulletins go out. New procedures are written. Engineers across the North Sea are retrained. The industry takes a deep breath. The cause has been identified. The fixes are in place. The Super Puma fleet is safe again. That is what everyone believes for the next 4.5 years. Now, before the second crash, there is a strange detail in the supply chain that almost nobody is paying attention to. The second stage planet gears used in the AS-332L2 and the EC-225LP are supplied by two companies. One is a German firm called FAG, the other is a French firm called NTN SNR. Both companies make these gears to Airbus helicopters' specifications. The gears look identical, they are interchangeable, but they perform very differently. After the 2016 accident, when investigators look back at the operational records, they will discover something unsettling. Of all the FAG-supplied second-stage planet gears installed in service, none of them ever reached the planned operating time limit. They were all scrapped during inspection before they reached the 4,400 flight hour mark. Among the NTN SNR gears, only about 10% reached that limit. None of these gears reached the intended lifespan. Something about the design or the loading was pushing these gears to the edge of their endurance. The engineering team at Airbus Helicopters knew when they upgraded the AS-332L2 epicyclic module for use on the more powerful EC-225LP that the new helicopter would put roughly 13% more power through each planet gear. They concluded the existing module could handle the higher loads without redesign. That conclusion would later be questioned. At 13 minutes past 11 in the morning on the 29th of April 2016, an EC-225 LP Super Puma, operated by CHC Helicopter Service, lifts off from the Gulf Fax B platform in the Norwegian North Sea. On board are 11 oil workers, mostly Norwegian, plus 1 British and 1 Italian. 2 pilots are up front. The captain is 44. The first officer is 57. Together they have over 17,000 flying hours. The helicopter climbs to 3,000 feet, levels off, and begins the routine run back to Bergen Airport Flesland. The weather is good. They are flying in daylight. Visual conditions. About 40 minutes into the flight, the helicopter is descending toward the coast. It crosses the small island of Turøy at 2,000 feet, doing 140 knots. It has been level at 2,000 feet for about a minute. There is no warning, no vibration that the pilots would notice, no alarm, no flicker on the instruments. A team of divers is on the rocks of a nearby island, preparing to enter the water. 2 of them are wearing helmet cameras. The cameras are running. The divers happen to look up because something in the sound of the rotor has caught their attention. What they see and what their cameras record will become one of the most studied pieces of accident video in helicopter history. The Super Puma is in level cruise, and then the entire main rotor head with all 4 blades attached separates from the top of the helicopter. The blades, still spinning, fly clear and arc through the air. The fuselage, suddenly weightless and unsupported, makes a half rotation to the right and falls. The captain has time to do nothing. The flight data recorder will later show 1 second between any indication of trouble and the end of the data. There is no mayday. There is no emergency. There is no chance. The fuselage hits a small island called Storskitholmen at roughly 45 degrees, nose down. Fuel from the tanks ignites. A white cloud of vapor expands and then explodes into flame. The wreckage tumbles. Pieces are spread across an area of about 180,000 square meters, on land and in the sea. The main rotor lands roughly 550 meters from the main impact. All 13 people on board are dead. Within hours, news reaches the British Air Accidents Investigation Branch and the Accident Investigation Board, Norway. The first investigators arrive at the scene before nightfall. By the next morning, oil companies and helicopter operators across the world have voluntarily grounded the EC-225 LP fleet. Within days, the AS-332L2 fleet is grounded as well. By summer, 80% of the world's Super Puma fleet is sitting on the ground. The investigation that follows is led by the Norwegian board. They reach out immediately to the British investigators who handled the 2009 crash. Both teams understand very early that they are looking at the same accident. The wreckage is recovered piece by piece. Divers from the Norwegian Naval Diving School pull components off the seabed. The main rotor head is recovered. The main gearbox is recovered. The epicyclic module is recovered. When metallurgists examine the second stage planet gears, 7 are intact. The 8th is fractured. The fracture surface under high magnification tells a story that is similar to the 2009 crash and disturbingly different. Similar because the failure mode is the same. A second stage planet gear in the same epicyclic module on the same family of helicopter has fractured under fatigue. Different because the crack did not initiate the way the 2009 crack initiated. In 2009, investigators determined the crack started in the loaded area of the bearing outer race. There was metal debris generated. There were warning signs. The chip detector on the 25th of March had caught some of that debris. The system, badly interpreted, had still seen something. In 2016, the crack started at a tiny surface defect, a micro pit on the upper outer race of the bearing, no bigger than a fraction of a millimeter across. The crack then did something unusual. Instead of growing outward, where it would generate detectable spalling and shed metal that could be caught by chip detectors, the crack propagated under the surface of the gear. It grew sideways and downward into the body of the metal, hidden from view, hidden from inspection, generating only a tiny amount of debris. The growth was under the surface. Norwegian investigators later wrote that the failure developed in a manner unlikely to be detected by the maintenance procedures and the monitoring systems fitted to the helicopter at the time of the accident. In other words, this crack was invisible. For somewhere around 1,000 flight hours, this gear had been cracking from the inside. The chip detectors on the helicopter were checked 6 times during routine inspections. 6 times, no chips were found because the crack was not generating enough debris to find. The fix from 2009, the improved debris detection, the additional checks, the redesigned procedures, none of it was capable of catching this kind of failure. There was one more layer to the story. The gearbox in question had been transported from a service facility about a year before the crash. During that transport, the truck carrying the gearbox went off a gravel road in Australia, allegedly trying to avoid kangaroos crossing the road. The truck rolled over. The gearbox was inside. It was inspected after the rollover. It was repaired. It was returned to service. Investigators could not definitively prove the road accident caused the eventual fatigue crack, but the timing and the unusual subsurface origin of the failure raised questions that the Norwegian board could not fully answer. The gearbox in question had only 1,080 flight hours on it when it was installed in the helicopter. By the time of the crash, it had 1,340 flight hours. That is a small fraction of the 4,400 hour operating limit Airbus had set. After the 2009 investigation, Airbus helicopters did not section and physically inspect any of the in-service second stage planet gears between 2009 and 2016. The recommendation to do so existed in the safety findings, but the physical disassembly inspections did not occur. As a result, the industry had no real-world data on whether subsurface cracks were forming in gears already in service. The Norwegian Accident Investigation Board's final report was published in July 2018. It goes deep into the technical metallurgy of bearing steel, of carburizing processes, and of the difference between 16 NCD 13 steel and M50 steel. It draws explicit comparisons to the 2009 accident, and it includes one sentence that, more than any other, captures the failure of the entire safety system. The post-investigation actions, the report says, were not sufficient to prevent another main rotor loss. In other words, everyone did everything correctly. The investigation in 2009 was thorough. The recommendations were accepted. The fixes were implemented. The training was updated. The procedures were rewritten. And it did not work. The crack mode in 2016 was, at the time of the 2009 investigation, not understood. Investigators in 2009 were missing essential pieces of wreckage that would have shown them subsurface fatigue could initiate from a tiny surface defect and grow invisibly. They could not see what they did not have. Worse, the 2009 investigation had focused so heavily on detection systems, on chip detectors and warning displays, that the underlying question of whether the design itself was robust enough was not given the same weight. The implicit assumption was that you could design a system that catches the failure before it kills people. The 2016 accident showed that for at least one particular failure mode, that assumption was wrong. The Norwegian board issued 12 safety recommendations. The most important one was directed at Airbus helicopters and asked the manufacturer to redesign the gearbox itself. Not another sensor, not another inspection cycle, but a fundamental change to the design of the part that had now killed 29 people across 2 crashes. The board also calls on the European Aviation Safety Agency, the European regulator, to revise the certification standards for large rotorcraft. The current standards permit single load path designs, where a single component failure can take down the entire helicopter. By the time the report is published, the offshore industry has already moved on. Statoil, the major Norwegian operator that contracted the crashed helicopter, decides not to use the Super Puma family again, period. Even after Airbus implements new safety measures and regulators clear the type to return to service, Statoil's contracts shift to the Sikorsky S-92 as the standard offshore workhorse. Norwegian and British civil aviation authorities keep a flight prohibition on the AS225LP and the AS332L2 for years. Some restrictions stay in place until 2020. By the time the type is allowed back into commercial offshore service in those countries, the offshore industry has effectively concluded that the Super Puma's working life as a passenger transport in the North Sea is over. The total fatalities across the two crashes is 29 people, 16 in 2009 and 13 in 2016. 29 workers and crew who climbed into helicopters they had every reason to believe were safe. Helicopters that had been certified by regulators, maintained by professionals, flown by experienced pilots, and reviewed by accident investigators after a previous fatal failure of the same component. The hardest question to answer about all of this is whether anyone in the system did anything obviously wrong. The pilots in both crashes were highly experienced. Their actions are not cited as causes. The maintenance engineers in 2009 made an error in following the troubleshooting card instead of the manual, but the documentation Eurocopter had given them was the source of the confusion. The investigators in 2009 wrote a thorough report and made strong recommendations. The regulators acted on those recommendations. The manufacturer accepted them. The system, in other words, did almost everything it was supposed to do, and the system still failed. 13 more people died because the failure mode in 2016 lived in a blind spot that the 2009 investigation could not have known existed. This is the uncomfortable truth that the Turoy crash report is essentially trying to articulate. Aviation safety is built on the idea that you can investigate a disaster, learn from it, and prevent the next one. That assumption has produced one of the safest forms of transportation in human history. Commercial aviation crash rates today are a fraction of what they were a generation ago, and a major reason is the discipline of learning from every accident. But the discipline only works for the kinds of failures you can detect. It only works if the conclusions you draw from the wreckage are the right conclusions, and it only works if the fix you implement actually addresses the underlying problem, not just the visible symptoms. The Super Puma story is what happens when all of those conditions are met, and it still isn't enough. The investigators looked at the right component. They identified the right failure mode for the wreckage they had. They drew sensible conclusions. They implemented sensible fixes. And the next crack that grew inside that same component in a slightly different way killed 13 more people. There is a small detail buried in the Turoy report that haunts the entire story. When the Norwegian investigators traced the operational history of every second stage planet gear ever supplied by FAG, the German bearing manufacturer, they discovered that not a single one had ever made it to its planned operating time limit. Every single one had been removed from service early, scrapped during inspection, or failed before reaching the 4,400 hour mark. The design, as installed in the EC225LP, was producing parts that could not reach their intended service life. That fact was visible in the inspection records for years. It was not flagged as a design problem. It was treated as routine wear. After 2016, Airbus removed the FAG gears from service entirely and reduced the operating life limit on the remaining gears to 1,100 flight hours. That reduction is itself a quiet acknowledgement. The original design did not have the margins it was supposed to have. The system was running closer to the edge than anyone wanted to admit. Two catastrophic failures, 7 years apart, on near identical helicopters, were the price of finding that out. For the families of the 16 who died off Peterhead in 2009 and the 13 who died near Turoy in 2016, this is not a comfort. The legal settlements were paid. The memorials were built. A steel statue stands by Quidi Vidi Lake in Newfoundland for a different North Sea crash from the same era, and similar memorials honor the workers lost from the Aberdeen and Bergen flights. The names are engraved. The flowers are still laid every spring. In Scotland, the fatal accident inquiry into the 2009 crash sat in Aberdeen in 2014. Engineers from Bonn, executives from Eurocopter, investigators from the Air Accidents Investigation Branch all gave evidence. One of the engineers who had been on duty around the chip detector finding admitted under questioning that the metal particle had been treated as fairly run-of-the-mill. There was no reason at the time, he said, for him to get involved. That phrase, run of the mill, became one of the lines that families of the dead would later quote in interviews. It captures something about how routine the failure of a system can look from the inside, even when, on the outside, that failure is about to kill 16 people. In Norway, the response was quieter and more institutional. Statoil published its own internal review of how it had handled the accident response. The review focused on emergency procedures, communication with families, coordination with regulators. It deliberately did not try to determine the cause of the crash. That was the Accident Investigation Board's job, and the board took its time. The helicopters that killed them sit in pieces in storage. The reports are public. Every aviation engineer who works on rotorcraft today learns these two crashes as part of their training. The lessons, finally, have been internalized. New gearbox designs in modern offshore helicopters incorporate redundant load paths and improved inspection access. The single point of failure that defined the Super Puma's epicyclic module is, in the newest generation of offshore aircraft, deliberately engineered out. But the people who died went into helicopters that were the state of the art at the time. They trusted the system. The system told them it had fixed the gearbox. The system was telling the truth as it understood the truth. And the truth was wrong. If this story stuck with you, the channel is working through every major North Sea offshore aviation incident in detail, and the next investigation is the one most people have never even heard of. Click the next video on screen to watch it now. If you have not subscribed, subscribe before you click. The next one is going to surprise you.